working with law of sines, you have to make sure that you're setting up. You have to make sure that you're setting up, and you have to have an angle and its side opposite in order for it to make any of it work. Now, when you start with one like this problem is forcing you to figure out what angle A is first. Because you've got
I have my homework in it, and accidentally left it.
Huh?
I accidentally left it in my other.
Anyway, it's fine. There's way too much to go through here today. I'm not doing this again. So, in order to make law of sines work, you have to have an angle and its side opposite. Well, we're almost there with this one. You have to figure out what angle A is. In order to figure that out, you have to subtract out the other two angles from 180, and that gets you A. And if I'm not mistaken, you get 95. Now, you have an angle and its side opposite. You need to use that angle and its side opposite in order to find the other two missing sides. When you do that, obviously we're using law of sines. So we know that we're going to have the sine of 95 is to its side opposite, as the sine of 70 is to its side opposite. Then we do that again for finding C. The sine of 95 is to its side opposite, as the sine of 15, in this case, is to C. Move this guy over. When you're trying to find side lengths, you have to cross multiply both. When you're finding angles, you only have to do one. That was kind of the difference between the two. So here, when you cross multiply both ways, you get B times the sine of 95 is then equal to 12 times the sine of 70. And this is, I think, where you messed up a little bit on that. When you look at that, you've got B times a crummy fraction, or a crummy decimal. How do you undo multiplying by a crummy decimal? Divide by it. So you divide by the sine of 95 to both sides. So your B value will equal all of that. You had it flip-flop. You see that? So I meant by you weren't cross-multiplying the right way? So you throw that in your calculator then, with your fraction bar. I get 12 sine 70 over the sine of 95. And I'm getting 11.32. You guys agree with me on that? 1132? So there's my little b. Then I do the exact same thing to find little c. Cross multiply over. Divide out. Twelve times the sine of 15 divided by the sine of 95, and I get 3.12 this time. You okay with that? I got 3.12. What'd you get? I might just bump to this. I mean, yeah, if you did this and you had that right on your test. Oh, I know you did. You read it as 3.176. You read there was an extra one on there. I wouldn't mark you wrong on that because I figured out, I could easily tell, oh, that's what you did. You did everything right, plus you wrote all this down correctly. So it could have been, I would have checked, I figured it out quickly, but let's say you had something weird. I would have said maybe you wrote down the sine of 50, like sine of 60. You showed me that you did it right. This isn't as important as this. Does that make sense? So that's a good practice. All right. What Alex did here, guys, And I just want to show you, just so you guys get the idea of why it's so important to write down what you're putting in the calculator before you do it. What he wrote down for his answer for this part is he wrote down it was 3.18. Now, if you look at your calculator when you type all that in, we have, what is it, 12 sine 15 over the sine of 95. When you look at your digits here, you can easily tell that he did everything right. But what did he look at it as? He looked at it as 3.17. He forgot there was an extra 1 there. So he showed me on his paper, he wrote all of this out. He did all of that work, and he just wrote 318 by mistake because he looked at the wrong part as he was writing down his digits. He's not wrong, because this is an easy thing for me to look at the number to figure out why he wrote 18. Oh, he just looked at 176. He rounded correctly, but he forgot about the first digit. So he's not wrong. He did everything right. That's the kind of thing that by you showing me what you're putting into the calculator before you do it, allows me to figure out what you just did. Okay? So knowing, and that's why we spent so much time about trig setups. Knowing how to enter it is just, if not more important, than knowing how to press a button. Okay? Does that make sense, guys, about why I always say that? This is a great example of the reason why to do it. He's not wrong. I wouldn't mark any points off. I'd make a little note, say you rounded the wrong spot, but you did everything right. Okay? I'm not out here to get you. Well, maybe you, but nobody else. Zoe, you. Other than that, there's like 3 or 4 of other ones I won't tell if I'm out to get. Because I don't like her sister. Because she's such a trouble. Just like you. Hellraisers. Those Maxwell kids are out to get you. All right? Questions on the first one? We okay? Second one. What's different with the second problem is that the second problem is asking you, basically, you have to find an angle first. This one, you had to find sides. The second problem, you had to go with angles. So let's see, we have A, B, and C. We have little a is 12, little b is 5, and angle A is 110. Now, this problem is forcing us to figure out which angle first. B. It's forcing us to figure out what angle B is, because we know we are given angle A and its side opposite. We're given that information. So what we're going to do from that is we're going to take it and use it to figure out what angle B is, because we know its opposite. So we started out, sine of 110 is to its side opposite. Sine of B is to 5. Now, if you remember, anytime that you're trying to figure out an angle, you don't have to cross multiply both parts. Because if I move the 12 over, I'd have to move it back eventually anyway. So the only part I have to move is the 5. Okay? So I move the 5 up. We get 5 times the sine of 110 over 12 is the sine of B. At that point, since you're trying to find an angle, you really don't need to do anything else but press buttons. Okay? You just start pressing buttons at this point. Fraction bar, 5 sine 110 over 12. I get some crummy decimal. That crummy decimal equals the sine of an angle. How do I find the angle? Inverse it. Very good. So I inverse my sine, inverse sine of my answer. I get 2305 for angle B. You okay with that? You get that one right? By moving those around? What? We supposed to laugh? Was it funny? Zoe did though, so what? What? Anyway, so you got 2305 for B. Now, what do you have to do to find angle C? Very good. To find angle C, after you use law of sines once to get an angle, all you have to do is subtract out from 180 the two angles you have so far to get the last one. So we go 180 minus the 2305 minus the 110. 4695 left over for C. And then I have to use that law of sines one more time to find the missing side one. Okay. So we have sine of 110 is 212. Excuse me. Okay. When you're trying to find a side length, you do in fact have to cross multiply everything to make it work. And then once again, we wrote out what we're going to press in the calculator before we press it in the calculator. Sine 4695. Sine of 110. Oops. $9.33. $8.77. I'm just curious if you did what I just accidentally did. You might have typed in a wrong digit somewhere. Did you write down what you're about to put in though? Yeah. I could probably figure out what you did just by. A lot of times when I can't figure out. A lot of times, guys, when you write stuff out and you said you had 8.33 or whatever it was, I would probably just try a couple of different digits, like things that bump next to each other, and I could probably find it within 2 or 3 tries of figuring out, oh, you probably did 4585, or instead of 46, or just something stupid. Just make it dumb. But if you have it written out, it's easy to figure out what you did. Okay. Law of sines. Now, going back to where we started all of this trig stuff, what was it, three and a half weeks ago now, I think? Something like that. When we started all, this is really kind of what you're going to want to start right now here, so you see where we're going with the to finish this out. The trig-o-rama super fun times. Trig-o-rama super fun times. Why not make up silly things for silly stuff? Now, guys, now when we go back to the very beginning of when we started this stuff out, what, 3.5 weeks or so ago, one of the things the very first things that we talked about was just plain old boring right triangles. And when you had a right triangle, we always did this first. When we worked with right triangles, the first thing we talked about was good old-fashioned boring Pythagorean theorem. Now, when you're dealing with Pythagorean theorem, it was how you found missing side lengths of a triangle if you knew two of the side lengths. Obviously, you had to have a right triangle to make it work, but that's what we did. We always kept things in our simplified radical form. You guys all knew how to do all that because it was super easy with the calculator. It's just a matter of setting things up. But after we did the right triangle stuff, we started to work it backwards. We started saying it this way. We said c squared equals a squared plus b squared. So we said this, if, or, remember we had these three different cases? Would be a very helpful thing. I mean, unless you know all of this. Sorry, I didn't mean to include you in that conversation, John. I forget you are all-knowing and all-wise. I know it was really hard for me to say that, too, with a straight face. So when we worked with Pythagorean theorem, we worked with what we called the converse of the statement, which basically meant we said it backwards. We said it this way. Well, first of all, of the three side lengths of a triangle, which one do we always call C? If we don't know if it's a right triangle, which one do we always call C? The longest one. The longest, the largest, whichever one it is. Okay. So when we did this, when we said it backwards, we said that if the longest side length squared was equal to the other ones squared, we knew it was a right triangle. Okay? That's just Pythagorean theorem in reverse. So if this happened, it was a right triangle. If that happened, what kind of a triangle was it? Obtuse, very good. And that's the reason why we write it backwards. I don't know if you remember this, but your textbook doesn't do it backwards. It does it the other way around. So it says if a squared plus b squared is smaller than c squared, then it's obtuse. Well, that sounds weird. It's smaller, but you're saying obtuse. So why not say it backwards? If it's bigger, it's obtuse. You know, I'm just trying to help you out remember stuff easier. I sense the sarcasm in your tone. I think she's getting lippy. What did you think it was? And then last but not least, if c squared was smaller than the other one, then we call it an acute triangle. Because it's lit. Now, the trickiest part of these things were the fact that you guys don't like to use your calculators correctly. For example, if you had the side length of 2 root 3 and you squared it, you would say that that equals 6. It would all be wrong. It's not. It's 12. So it's things like that that you just have to be cautious of when you're working with these things. That if you've got radicals in the problem, you always put things in parentheses before you square. Okay. That was one of those tricks that you guys tend to always like to screw up. Right? Yeah, give me a sec. Because somebody didn't give them back to me yesterday and just left them lying there without saying, "Oh, thank you."
That's crazy.
Oh, let's not do that. It's Jackson. Come on. See, thank you and give it back next time. Thank you. Anyway, after we did all that, we switched into the specials. We had the two special right triangles, which all everything else after geometry is based off of. Your special right triangles. Again, it seems like this was forever ago, but it was your 30, 60, 90. Yes, ma'am. And your 45, 45, 90. And when we dealt with these, we dealt with those special right triangles. We worked through the problems using what I call here this algebra jig, if you will. And what that meant was you had the same kind of setup problem over and over again that you're working with ratios of sides to try to solve out. Depending upon what part you were getting, it told me that that angle of 30 was looking at some value of x. The angle of 60 was looking at some value of x times the square root of 3. The angle of 90 was looking at some value of 2 times x. You had to sit there and look at your problem to work backwards out of it to figure out what exactly you were working with. For example, if I have a 30, 60, 90 triangle, and let's just say we happen to be given across from the 90. Now remember, that means, and this is why we kept using these arrows to show that you're looking at something, that means your side opposite you. That's where all that started up. That means the 90 is looking at some value of 2 times x. Well, that 2 times x happens to equal 18. So how do you undo multiplying by 2? I hope you do. So that means that everywhere I see an x in the rest of that algebra jig, what do I replace the x with? A 9. And I go on my merry way. Okay? Both of you guys. Same thing worked if you were given across from the 60. If you're given across from the 60, you just had different math to work with. Let's say across from the 60 was 12. If that part was equal to 12, that means the 60 is looking at a segment that's something times the square root of 3. Well, that time it equals 12. So in your calculator, how do you undo multiplying by the root 3? So you type it in. When you do that, you're going to get 4 root 3, I believe. Or use your calculator so you can verify. That's, again, what the value of x is going to equal. So everywhere I see an x now, I'm going to replace it with 4 root 3. Just like we've done in the past. That doesn't change. You're using those ratios to work yourself through that algebra jig of a problem. It didn't matter whether it was the 30, 60, 90 or the 45, 45, 90 on how you would solve and set up stuff through. The only thing that changes were the ratios. So if you had a 90, if you had a 45, 45, 90, there was a whole nother setup. Let's move this over here. And why is that a 45? Very good. That one's isosceles. It's an isosceles right triangle, which means it has to be a 45, 45, 90. So let's just say we know across from a 45, let's say it's the square root of 6. Okay? So remember, as you work through stuff like this, if you know that the value across from a 45 is, well, in this case, square root of 6, that means everywhere I see an x, what do I replace it with?
Square root of 6.
Square root of 6. And then in my calculator, I just have to type in the square root of 6 times the square root of 2. What's 6 times 2? Square root of 12 is? Obviously, it's 2 root 3, which means you better have your calculator ready. Okay? That's the kind of stuff that we did. We did this over and over and over again. It was the same ratios time and time again. Okay? After we got through the specials, that's when we started doing trig. And I think for the bulk of the past 2 weeks, it's been basically straightforward, regular, boring SOHCAHTOA. And when you're dealing with SOHCAHTOA stuff, that means you have to know what that stands for. How's that? What's that? Op, edge, op?
I like English.
No.
What's yours?
The A and C are close to the S or O.
Oh yeah, I remember that. I actually wish that they would say, I wish they would do the cosine stuff first, because when you get to algebra 2, cosine goes with x coordinates, sine goes with y coordinates, and that, by saying it this way, we're saying y then x, and then next year we go x, y. Anyway, so we know that sine and no, we're not getting note cards. Okay. And as we went through all of these things, it was just a matter of, we always wrote it out like this as perspective, depending upon what values you were given and what you were looking at. And I know that you guys are really good at the setups. So if you go back to that one quiz we took a long time ago, where you had to write out the ratios of sides, your angle always looks at what? The opposite. The angle that you're dealing with will always look at an opposite. The hypotenuse never changes location. That will always, always be there. So if you're able to circle with whatever angle you're dealing with, know that it looks at an opposite, you know that the hypotenuse never changes location. By process of elimination, what's left? Adjacent. Good. And that's kind of what we did a lot. Okay? For example, if we had a problem where, let's say we have 41, and we'll call this A, B, and C, and this is 13. And I need to find all my missing side lengths and all my missing angles.
Right now?
Well, yeah, all right, fine, go for it. But remember how we did this, though? When you had a setup like that, you had to solve for everything. I'll put it on clean one. Give me a second here. I gotta get this stuff going. Okay. When we did these types of problems, I always asked you guys did what? Right, but if you had to solve for everything, what did you have to write down first?
The opposite.
No. Back up. What do you have to find in this problem? Write down what you have to find. Yeah, write down the sides you have to find and the angle you have to find. That's what and you guys aren't wrong by circling your angle and doing all the other stuff, but you got to know what you're going to find first. So when we did this, we said, okay, write down the stuff you had to look for so that way you didn't forget what you had to look for.
Well, I mean, we stopped doing this.
No, we've been doing this for a while like this. When we were solving all of our right triangles, we kept doing that. We kept writing it out, remember? Even towards the end of last week before we got to elevation depression, you were still writing out what you had to find. Okay? So what's the easiest thing to find first? Angle A. Why is angle A the easiest to find?
Because,
Right. Now, hold on. Would I ever use angle A to find anything else in that triangle? No. Why? Not just the inside outside. It's what happened when you screwed it up. Never. Guys, why am I talking over this? I'll give you the test tomorrow. I'm giving you the opportunity to review for a couple extra days. This is not the biggest stuff. This is not an easy setup. Shouldn't have to talk over it. But the reason why we don't worry about reusing stuff that we've done is because what if you screw up? We never want to reuse anything that you find to find something else. The only time we have to do that, or the only time it's really feasible to do that, is if you wind up working with law of sines, because law of sines, you kind of have to. With this stuff, you don't. Okay? So the easiest way to figure out angle A, like you were saying, is to subtract out and get it out. Get it that way. So angle A, I believe in this case, gets what, 77? Okay. So then I go back to what we know. Circle the angle that you're given. That side there is mine. 41 is mine. Process of elimination. So if I'm going to find my opposite first, what trig function is opposites and hypotenuse? Sine. So sine of 13 is our opposite, AB, over 41. When your unknown is in the numerator, what do you do with the denominator?
You turn to 41 to sine 13.
Very good, very good. So you just use your calculator, you write it out. It's going to be 41 times the sine of 13. Okay. When I use that to find the adjacent, knowing the hypotenuse, what trig function will that be?
Cosine.
Opposite hypotenuse. We're not trying to find that, we're just trying to figure out what those two parts are. Adjacent over hypotenuse. So then it's a matter of pressing buttons on the calculator. But again, you're writing down what you're going to do before you do it. Yes, ma'am?
Well, since you asked 77, I put cosine 77.
What if you screw that up? What I'm saying is, what happens if you wrote down 87? Correct. Never use something you found with right triangles. Always use your givens. Just like we always have said. I've always said that. I don't want, I'm taking the possibility of screwing something up twice away from you. So whenever you have this, always just use your given information to find the missing parts. Whenever you have right triangles, use your given information to find it. Don't use stuff that you found. Because what happens if you accidentally subtracted 13 from 100 as opposed to 90? You know what I mean? You'd always be wrong. Whereas if you did one of them, if you did this, let's say you did the sine of 13 and 41, but then you got an answer, but let's say you accidentally did cosine and you flipped it. Even though you have the same values, you could get one right and one wrong, or you could get them, by using the givens, that kind of stuff. So you just want to stay away from that. Yes, sir. It should be.
Yeah, that's all.
Yeah, it will be. Yeah, and it will be for stuff like this, because if you did this correctly, since you're not doing any major rounding there, you're just subtracting from 90, you're not gonna have a problem. But when you start getting into the a problem like this, where you've got your the two side lengths, let's say this is 12 and this is 17. Once you start rounding stuff out to find your angles, because they're not going to be clean, you're going to be further away from other answers. We're talking hundredths, but it's better off not to do that. Does that make sense, guys? Always try to reuse your given here. I mean, whenever I have something like this, in this case, what trig function am I going to use to find angle A? What trig function am I going to use to find angle C? Tangent. A is going to be the tangent of A will be 17 over 12. C would be the tangent of C would be 12 over 17. And that's okay. They can flip like that because they will. You get stuff like that. After we did that, we switched back into elevation depression. And we did elevation depression stuff. It wasn't terrible. It was just a matter of drawing pictures. Okay? So let me give you some pictures here.
Sorry. One second. One second.
the fact that he's super happy about, only having 4 fingers and 4 toes. It's kind of fun. This is what we're doing. So what I've done here is I've kind of pieced together a whole bunch of different types of problems and whatnot that we've looked at. It should be in that binder if they should be in there somewhere. If not, they might be already all gone. As you go through stuff like this, these are problem sets that are basically in every single section that we've talked about over the course of all the trig stuff. And what I wanted to do real quick is kind of jump back to a few things that we've done recently, which haven't been so difficult, talking about like angle of elevation. So flip over to the 3rd page there. I want to take a look at number 8 on the top. On the 3rd page. I apologize, there's 2 7s and 8s and 9s and 10s. While you're on that 3rd page, I want you to go on the bottom of it real quick. Those bottom 6 triangles are all law of sine style. They're all law of sines. Go ahead and cross off the first 2, 7 and 8 on the bottom there. The bottom 2 triangles, 7 and 8, because there are 3 of them where you have to find 2 angles and a side, and there are 3 of them you have to find 2 sides and an angle. Why not make it 2 and 2 instead of 3? Not a big deal. Once you even do it a couple times, you don't have to keep going. It was one of those quick cut and paste things that I just threw in there. So if we take a look at number 8, those first 4 problems at the top of that page are of the complexity of the stuff that we've been doing. Not too bad, nothing too crazy. It's just kind of a quick picture of what something looks like. So if you have a pole that's a vertical post that's 15 feet tall, what does that look like? Something standing straight up, because it says it's vertical, that happens to be 15 feet tall. Where do shadows lie? In our case, we'll say it's on the ground. And it says, what is the angle of elevation of the sun when a vertical post? It means we have to find the sun, it's going up this way, to the sun. He's wearing sunglasses today. Why wouldn't you? Sure. So when you're looking for the angle of elevation to the sun, you're looking up. What trig function gets you that? Tangent. Very good. We'll use tangent for that one because we're looking at, in this case, we have a theta looking up to the sun. We know the vertical post is 15 foot long. We're at the end of the shadow that it casts. That's 20. So we know our opposite and our adjacent. So we know that the tangent of something is 15 over 20. Inverse? What, Olivia? That's just an angle. It could be anywhere. It depends on the problem. Okay, because sometimes we have the angle of depression. Sometimes it just depends on where it goes. This is saying it's looking up to the sun, so I just put it from the. It's going from the ground to the sun, so that means it's going to be in that location. Okay. So, like Alex said, shh, guys, in order to find your value of theta or the angle, whenever you're finding an angle, you have to use the inverse button. Whether it's sine, tangent, or cosine, you're still using the inverse button to be able to do that. So in this case, you just write down what you're about to type in the calculator and go. In doing so, you get what? Inverse tangent of 15 over 20. I think that was what I had earlier. 3687. is the degree looking up to the side. Okay? I'll get to that here. Now, excuse me. What I wanted to show you guys real quick, flip over to the back page. Now, what I was trying to do with compiling a bunch of extra problems here was that I was just basically cutting and pasting from some old worksheets and things that I had lying around. And honestly, the only things that I'm looking at being able to really kind of go through here on this back page are numbers 1 through 7. Numbers 1 through 7, the first 3 are just Pythagorean theorem. The middle 4 there are what kind of a triangle is it? Is it right, acute, or obtuse? That's when you have to figure out which one of the 3 is the longest. And I kind of ran out of those problems. That's why I found those 4, and I knew we hadn't done them yet, so I'm like, oh, let's use those. The ones on the 8 and 9 are things we've never done, so I'm not worried about it. But if you look at the bottom 4, or excuse me, the bottom 8 problems are just special right triangles and trig functions. Those are simple. I know you can do those. Those are just extra ones there. Now, what I've done here is, if you go to the front page, let me give you a hint on certain things I would do. Page 1. 1 through 4 is just Pythagorean theorem. Whenever you're trying to find a missing side length of a right triangle, you're just using Pythagorean theorem. After that, it's your specials. And you have to know these ratios. There are a lot of bits and pieces of things here that you have to be able to do. When you get to the second page, the first 8 on the second page that's all self-control. Those first 8 are all SOHCAHTOA. The last 4 are the ones where we would use the special right triangles into 2 different triangles. And we'll spend more time on that tomorrow. I'm just going to say it's specials times 2 because you have to use specials twice. You have to work your way around the triangle. That third page I've already talked about. It's elevation and depression. The bottom is law of sines. Can I write to a clean page, or I'll just do this? And then the last page, like I said, was just Pythagorean theorem and then converse. Yeah. Mm-hmm. Okay. What's that? What I want you guys to have done for tomorrow are pages 1 and 3. Okay. The ones with the Pythagorean theorem and the specials, elevation, depression, and law of sines. I figured that's a pretty quick setup to make them through. I don't think that should take us more than 15 minutes really to get those 2 sets done. And then tomorrow we'll start the day reviewing the depression and law of sines stuff. Then we'll switch over to the specials, because then we'll use the specials from 5 to 10. Make sure we know how to do the specials in 1922. Yes, sir.
So, on the first page,
Whoa! Yeah.
Number 2.
Yeah.
It's like, so when you square root it, you square.
Yes.
So, 2.
No. What do you calculate? You did it wrong. You gotta put parentheses around it.
I put two parentheses.
Yeah, you gotta put the whole thing in parentheses. Yeah, whenever you have roots, hey guys, this is a great question. Whenever you have square root stuff and you're trying to square it with a number in front, you have to put it in parentheses, okay? Yes, ma'am.
Okay, so 1 and 3 or 1, 2?
1 and 3. All right. Ellie, you had a question or no?
Yeah.
1 and 3. Yeah. Those shouldn't be so bad. I honestly don't think. I think the ones that take the longest might be the solving the whole triangle out. Because a lot of science should be pretty quick by now. It might be 20 minutes. Yeah, that's my guess. Okay. You'll get over it. Your days become shorter and shorter and shorter the further you go in high school. Yeah. I mean. What's up, bud? Okay.